Sophia. Mm. Hey everyone, it's 10 o'clock, which means I can start talking. Welcome to section today. So, overview. I have a few announcements and then we'll kind of go into section things. I've started meeting with several of you all, doing our like little 10-minute meetings. They've been going well. And if I come off as rude in the meetings, I'm not trying to be rude. It's just we have 10 minutes, so we have to be very like in and out. We're diagnosing what's going on. We're giving like concrete suggestions. We're making action items. So if I'm like kind of short with that, it's not like a trying to be rude thing. It's trying to be like, how can I help you the most in 10 minutes? Several of the meetings so far, they've been going well. I will say that there have been more like cancellations / no-shows than I've expected, which is totally fine. Like it does not matter to me, but I just have no other availability this week. So like if you miss your slot and want to still meet, I can try to meet with you next week before the exam. But like I just don't have any more availability this week because she's packed. She's booked and blessed. Survey. I think y'all are now up to like 70%. So a lot of people did it. I'm gonna send out an announcement, I think, after this section, being like, hey, this is the current percentage you're at. Reminders, do men don't. So peer pressure your friends. Yes, and then we'll try to kind of implement and respond to some of that feedback on Thursday and Friday. The other thing is my section notes are a little bit rough today. So they're a draft, they're a mixture of some new things. And it's because I spent all my time on this reaction web, but like you'll see some of these look like my normal section notes. Some of these look like a basic, like lower version of what I normally do. So sorry about that. I feel very much like a sign of like, please pardon our appearance. We're making renovations to better serve you. So it's kind of this weird mixture. But this is what I spent on my time. So thank you. Thank you. So yes, like she did take many an hour. And she's had a glow up over the years. Like she used to be handwritten, and then I made her digital last year, but she was like boring. So like last year, I think she looked like last year she was her, and then just before, after, before, after. Wow. Wow. So this I think is going to be the big kind of tool that's useful for y'all. Whoever wrote I hunger for review sheets on the review, because someone wrote it that way, this is for you. Yes, I hunger. So what we're going to do today is we are going to break down the alkene reactions. One I'm not going to talk about is the radicals, because we're going to do more radicals in lecture 9. So we're going to talk about radicals in section 9. So that's coming. But to just kind of orient you here, I think about the alkene reactions as divided into kind of two big families. So the red ones through the dark blue ones here, everything on the right side, I call these the simple alkene additions, because these are kind of more basic and have like more straightforward mechanisms. And also these are the ones that we are going to test you on more for mechanisms as well as the line reactions. Now, the left side over here, these are great reactions. They're lovely. But the mechanisms are so weird that we probably are not going to ask it as a mechanism question. Like you're going to have a lot of like step 1, do this weird arrows you've never seen before. And then step 2, don't do the mechanism. It's too scary. So like that's not going to make sense for that to be a mechanism problem on the actual exam for us. So these ones on the left, I call the complex alkene additions because they're a little bit weirder. They're a little bit more intricate, but you only really need to know them deeply at the line reaction level. So that kind of like, it's a trade-off of what we're focusing on. And then within each one, each color kind of represents a family of reactions that we're going to talk about, like a subfamily. So if we think about overall, we have the alkene family, the extended family, like they're all cousins. And like this is one immediate family, this is another immediate family, this is another immediate family. And they all kind of are at the reunion together. That's like the vibe of the alkene reactions. Yes. I also am running on very little sleep, and so I've been making like careless mistakes, and I'm like, I start talking, I don't know where my point's gonna be, where normally I know where my point's gonna be. So if I get confused, if I make a mistake, please bear with me, and please call me out. You know, I'm here for confrontation. That's how I like to teach confrontationally. So before we can really jump into the alkene reactions, we need to kind of set up some terminology. So the big idea here is for each of these alkene reactions, when you were studying them and when you were learning them, you have to ask 3 questions and get the answers for each of the reactions. So you need to know what is added to the double bond. You need to know where it is added on the double bond, and you need to know how it is added. So let's kind of get into those questions a little bit more. So when you have an alkene, you have a carbon-carbon double bond here. And when you get rid of that double bond, you need to make 2 bonds to replace it because each of those carbons needs something on it. So we are typically going to be adding 2 things to the alkene in each of these reactions. And so like this will also typically form a distinct functional group that's helpful. So when we go over to our sheet here, I've written, okay, this reaction adds an OR and an H, and it makes an ether. This is kind of telling you the identity of the reaction. What are the things that we are adding to the alkene? Why do we have this reaction around? And some of these are weird names, like a vicinal dihalide. That feels like very snooty, like hoity-toity. But like it's helpful to recognize that this is a thing that is formed from this specific reaction. And so like you don't need to know the names, but you do need to like clock her when you see her. If you see these neighbors next to each other, know it's probably an alkene reaction, and then know which reagents to get. So part 1 is the what are we adding to it? Then part 2 is where are we adding? So Tim mentioned it briefly, but we have this concept of regiochemistry, whereas it's kind of like when we have 2 options of where to add something, where we specifically add. So the regiochemistry for most of these alkene reactions follows what's called Markovnikov's rule. Markovnikov's rule is the more substituted, or the more electronegative group adds to the more substituted side. And can we repeat that together? The more electronegative group adds to the more substituted side. The more electronegative group adds to the more substituted side. One more time, but like soft. Okay, that was still a little, that was like a mezzo forte, mezzo piano. I wanted pianissimo, but we're getting there. We're getting there. So Markovnikov's rule. Typically, the more electronegative thing is going to be some sort of nucleophile. And also in a lot of these reactions, the less electronegative thing is going to be some sort of hydrogen. So if you add your nucleophile to the more substituted side of the alkene, the one that has fewer H's on it, then we say that we formed the Markovnikov product because we follow the rule, the more electronegative things added to the more substituted side. But if we form the product where we add the more electronegative thing to the less substituted side, we call this the anti-Markovnikov product. I don't know why, but my association with anti-Markovnikov is like, I hate Markovnikov. And it's very the attitude of the film John Tucker Must Die. Markovnikov must die. I'm anti-Markovnikov. Again, I don't think it'll help you, but it's just how I think about it. And so every time I think Markovnikov must die, he probably did die. But for each of these reactions, you'll go through and you'll see most of them are Markovnikov reactions. And then some of them are going to be specifically anti-Markovnikov. And so knowing which one of those are anti-Markovnikov will be important for you. Some of them I put in air quotes. Why did I put Markovnikov in air quotes here? If we added OHs on both of them. Yeah, so there's no more electronegative thing to add to the more substituted side. They're equal. You're adding the same thing to both of them. And so I put Markovnikov here to be like, she's normal. You don't need to worry about her. Like, you don't even have to think about her. It's really the anti-Markovnikov ones that you have to look out for. So that is the regiochemistry. Where are we adding? And then the last question is, how are we adding? So I have an alkene here. Do you see the alkene? She's here in front of us. Now, we have our p orbitals that are perpendicular. So like one p orbital is kind of going up and down this way, and one's kind of going up and down this way. And when a molecule comes along to react, I'm just going to do like, come along to react. When we add the things, we could add both things up on the molecule. So we could go from this alkene to two things come along and they both added on the same side up. Oh, I should hold it this way, right? So do we see how we have this alkene and then we added these two green things and they're on the same side? Then we say that that is a syn addition. If we did it like blah, 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 here, again, we have our alkene in the same kind of orientation and we've added our two things from the same side but going down. That is also a syn addition. It's just adding on what we call the same face of the alkene, the top or the bottom face. And I'm trying to kind of draw it visually here of like here, you can have it two down and that translates to two on the wedge over here. And then two up, or sorry, see this is the thing. I'm tired and so I'm just making weird like verbal things. Here, two down are going to be two on the dashes. And then two up are going to be two on the wedges. So we could add one up, one down. The other thing that we could do is an anti-addition. So you have your alkene here, you have the product where you've added something here. And now the purple ones that you've added are one up, one down. So if one adds on the top face, one adds on the bottom face, we say it's an anti-addition. So we can either have it like left up, right down, or left down, right up. Either one works. But the big thing is one's on dash, one's on the wedge. Now, we just said anti, but we also had anti over here. So a really common things that students get tripped up on are thinking an anti-addition for the stereochemistry is like anti-Markovnikov, and they truly just use the same word and they're talking about the same topic. So it's just like a confusing nomenclature thing. But typically, if we say anti, we mean stereochemistry. We mean, are they adding on opposite faces? Versus if we want anti-Markovnikov, we have to say anti-Markovnikov. Last thing, you're going to have some reactions where you get a mixture of the syn addition and the anti-addition. So you get some where you add both on the same face and some where you'll add on opposite faces. In which case, we just say that we get a mix of syn and anti. And so you'll see over here, several of these I've written mix. So these questions I've answered for all of the reactions for you. So you can just like look at them and hopefully that is doing some of the work to kind of like consolidate it and make it feel a little bit more digestible. The other thing is we're doing a lot of work right now with like wedges and dashes and stereochemistry, but oftentimes it's going to be easier for us. Like I'm choosing to show you a hard version. So like here, this alkene, if we add R1 and R2 here, why do I not need dashes or wedges on this? No stereocenters. This is attached to two methyl groups, so that's not a stereocenter. This is attached to two hydrogens, not a stereocenter. So if we don't have a stereocenter, we can just ignore her, really. But for the more complicated cases, we do need to have these tools to be able to talk about it. So do you have any questions about these words that we use to talk about alkene additions and these kind of questions that you'll need to answer for yourself as you are studying each of these reactions? Ooh, oh, Abby, hi. Well, the thing is, it's not that it's planar, it's that writing on a wedge or a dash doesn't tell us anything new. And so, like, it's kind of like saying, I'm trying to communicate this IDEA to you, and like you get it, but like I just spelled it out when I could have just said it, you know? Like it's just the difference between here, you're making really clear that you know it's not a stereocenter. But if you put on a wedge, it's not wrong. It's just like spelling it out versus saying the word, you know? Yeah. Other terminology questions? Groovy. I will say the first part of section today is a lot of me like talking and getting through ideas, and then we do like a batch of problems. And this is because I didn't have enough time to rework it. Normally I'm going to try to integrate it a bit more, but here you're just going to hear me talk for a little while, which is a little much. So let's talk about the first family within our big alkene family. So we have simple acid additions. So the mechanism for all of these is the alkene is going to go and grab a hydrogen from something, some acid. You could just do it as like H+. And then you form a carbocation. And what do you know about carbocations? I'm going to need a little bit louder. Rearrangements. Carbocations do funky things. So you always have to be on the lookout for forming a more stable carbocation. And at this point, some nucleophile is going to come along and attack that carbocation. And the nucleophile is going to be more electronegative than the hydrogen. And so we have the Markov-Nikov addition. We've added the more electronegative thing to the more substituted carbon. So let's talk about like this kind of mixture of stereochemistry products by using this example. So this alkane. She's kind of wild and crazy. Do you guys remember what D is? Thank God, okay. Deuterium. She's just an isotope of hydrogen in a way that we can like label a hydrogen and like not get it confused with the general hydrogen. So if we do our first step where we're adding the H is going to add to the less substitute side. Why does the H add to the less substitute side? I heard like sterics and electronegative. Talk to me about this, girl. So if the H adds to the less substitute side, then which side gets the positive charge? The more. And what do we know about carbocation stability? Is it going to be more stable with a more substitute carbon or less substitute? More. Good. You're totally right. So we're going to add the hydrogen here. But like we said over here, if this is our alkene, our hydrogen could add from the top, and then it would be on a wedge over here. Or our hydrogen could add from the bottom, and then it would be on a dash over here. So we have two options for this first intermediate. And then after that, when we have our carbocation, we know that this is planar. And our nucleophile could either attack from the top, in which case we'd have both of them on the wedge here, or our nucleophile could add from the bottom, in which case we'd have the nucleophile on a dash and our hydrogen on a wedge. And the same exact thing is happening over here. So what we get is we have a mixture of 4 diastereomers in the products. And because we have all this complexity, we would have to write all 4 of them as the answer. One thing that we can do to like save us some time is, do you remember us talking about the plus minus before? So a plus minus means that we have the molecule and it's an enantiomer. So like, which one is the enantiomer of this one? I'm going to do 1, 2, 3, 4. 3. It's when all the dashes and wedges swap, we get the enantiomer. So I could write this one and plus minus, and that would save us from drawing one of the structures. And then if I wrote this one, its enantiomer is going to be the one down here, right? So I could erase this one and put plus minus. And this would be the complete answer. But if you did not have both of these for this question, we would have to take off. This thing where you're forming 4 products only happens with these acid additions because they do the mixture of syn and anti, and you have the carbocation. So this one's like the biggest pain in the butt. But also most of them that you do are not going to have 4 products because they're not going to both be stereocycles. Like if I made this an H instead of a D, then it would be H and H, and this is not a stereocycle. So that automatically like eliminates 2 of these that we don't care about. Does that make sense in terms of listing all the products of the stereochemistry of what we're going to get out of these? Are there questions on this? Yeah. When you have 2 stereocenters formed from this like alkane addition and acid, you'll get 4. None of the other ones you'll get 4. This is the only one. Or this is the only family. So we talked about, we always have to check both ways when we form a carbocation for rearrangements. So if we have a secondary carbocation form next to a quaternary carbon, we'll have like a methyl shift happen. And then we get our nucleophile added here. So if we wanted to add our nucleophile here, we would need to find another route to do it because this is not going to work. So because of that, these reactions are pretty limited in terms of what you can do on synthesis, because you'll get carbocations and they can rearrange and they will get products that you don't want and have all these diastereomers. So this is much more heavily tested as a mechanism question rather than a line reaction for like synthesis. But let's talk about the specifics of it. So for each of these, we're an acid because we know our first step is the alkene goes and grabs a proton. But then we have our second step up here where the nucleophile comes in and attacks this carbocation. So can we just list out what are the nucleophiles for each of these reagents? So if we have HBr, we go and grab the H, and then what's the nucleophile that attacks the carbocation? Br minus, yeah. And then for HCl, it's going to be the same thing where we have Cl minus. What about for H3O plus? What's the nucleophile that's going to attack? Ooh, controversy. How many people think OH minus? How many people think H2O? I'm so sorry. You've been voted off the island. You can pack up. I appreciate you. So the reason why we're going to do H2O instead of OH minus is because we're an acid. So we're not going to have like a OH minus, like that's kind of removing 2 protons from it. But our nucleophile will be water. And so when we have that step where we have the carbocation here and our H2O attacks, we will need one final deprotonation step here because we'll have protonated this and we just need to take out the hydrogen to make it neutral to get into our product. But that's stuff that at this point you can do with deprotonation. Like, and I don't have to write it out explicitly for y'all because I think y'all are getting it. Now, if we have alcohol, then instead of H2O as our nucleophile, it's just our alcohol as a nucleophile. It's going to do that type of step. And so we get a variety of products. I will say on the review sheet, because we had a weird number of reactions, I just called this one reaction as like HX. So like if you did this HBr, you add a Br. If you did HCl, you add a Cl. But it's just being like, hey, you don't need to think of these as 2 separate reactions. This is truly one reaction. Just you replace it with whatever halogen. Is that vibe check feel okay? Great. Okay, moving on. This first family was the simple acid additions. Then we have the X2 anti-additions, which I don't have a cool name for her. I was trying to think of like X2, like dihalide, double agents, blah, blah, blah. I don't know. So if you come up with a better name, let me know. So the mechanism here fundamentally is different from the first step. So what we have is this pi CC attacks the sigma star halide halide. So the BR-BR CLC CL bond. Now, when we put electrons into an antibonding orbital, what happens? The bond breaks, which is why we have the second arrow. And then at the same time, instead of forming a carbocation, because our halide has these lone pairs that are big, and because it's coming towards that alkene, what it's going to do is it's going to go and attack the alkene and donate into the pi star CC. And oh my gosh, wait, that means the pi bond's breaking. And so those electrons are going and attacking, like it's this whole like closed circuit where you're like attacking this, but the electrons that came from that are because you attacked this. And so this is a concerted mechanism. You're going to start to see more of these concerted mechanisms in this lecture, especially. But I think they're really cool because the electrons are just like, I jive with you. We're going to do a circle. So when we do this, instead of forming carbocation, we form a cyclic bromonium or cyclic chloronium. So it's just a 3-membered ring with a Br or a Cl. What functional group does this remind you of? Epoxides. So remember when we talked about epoxide openings, we said that if our epoxide was like up on a wedge out of the plane, we had to have our nucleophile attack from the bottom because that is where antibonding orbitals are. And we are breaking a bond, so we have to attack the antibonding orbitals. So the exact same thing happens here. So when our nucleophile attacks and we form our cyclic bromonium or chloronium on a wedge, the nucleophile is added on a dash. If our like cyclic bromonium chloronium, I hate saying that, is on a dash, then our nucleophile adds on the wedge. And so this step should remind you almost exactly of the epoxide openings. Cool. Questions about this mechanism so far? Yeah. No. With the plus minus, you need to draw it specifically one way. And then the plus minus says you have that specific way and the so like here, I didn't use plus minus, but if I did want to use plus minus, what I would do is I would erase these. I would put a plus minus at each of these steps. Yes, or I could erase these and put a plus minus here. It does not matter which one you do, but you have to draw a specific one and then use the plus minus to say it's an adhesive. Yeah. We are going to get to that. Yes, that's a great question. So typically, so let's say we just had our dihalide here. Then we're going to have another X come along and attack. And then we've added 2 X's. So is this Markovnikov or anti-Markovnikov? It's Markovnikov because we're adding the same thing to both sides. So we don't have a difference. Like here, this would be adding a Br and a Br or a ClCl. So like there's no difference. You're adding the same thing to both sides. But the important part here is the stereochemistry here. So because if your cyclic bromonium is on a wedge, you are adding on a dash over here, or if you're on a dash, you're adding on a wedge over here, you're always going to get your nucleophile and your halide opposite each other. So they are always going to be an anti-configuration. And again, this anti-configuration comes from the fact that you form this kind of epoxide-like three-membered ring. Yes, and so that's why these are the X2 anti-additions. So now, if you just did it with Br2 or Cl2, your nucleophile in the second step that attacks is just going to be Br or Cl, because that's the other thing that you add. So these are the nucleophiles that we are using for these reactions. But we can do interesting things with solvents here. So imagine you did this reaction in water, where you had a Br minus, but you also had you also had like maybe many trillion water molecules. So the options for attacking are one of many trillion water molecules or one load bromine void. Who is going to be the one that actually attacks and adds? H2O, just because it's a numbers game. So what you get here is when you do the reaction in water, the nucleophile that adds in the second step is H2O, and then you deprotonate it and get OH. And so the functional group that you have here is a halohydrin. Remember about halohydrins from lecture 7? They make epoxides. Store that for later. We're going to come back to her. So, okay, if we want to have a halohydrin here with bromine, what we use is Br2, forms the cyclic, and then we have H2O come and attack. We're a halohydrin. We can do the same thing with chlorine. So our nucleophile in this case is also H2O. And then the exact same thing happens if we are in alcohol. So our nucleophile that attacks ROH. And so just doing it out very quickly, we get to this step. Our ROH would come attack the more substituted side, kick off the bromine. What we would be at is this structure right here with a plus, and then we deprotonate it. Does that mechanism feel okay? And does it seem like it's a direct variant of everything we've done before? Cool. So this is the thing where like technically these are 6 reactions. But really you should think of this as 3 reactions. And really they're all variant of 1 reaction. So it's finding these patterns of all of these have the exact same mechanism here. And we're asking what is the nucleophile? And then the way I abbreviated them on the tree, I put this is 1, this is 1, this is 1. Yes. That's exactly what I was about to ask. So we added an OH and a BR. Which one's more electronegative, OH or BR? OH? Was OH added to the more substituted or less substituted side? So we added our more electronegative to the more substituted side. And oh my God, that's the phrase we were chanting earlier. We did Markovnikov's rule. So we did a Markovnikov addition that had anti-stereochemistry, which is not anti-Markovnikov. I'm just saying, like it is confusing. So like if you are confused, that's valid. But yes, we're doing a Markovnikov addition and we're doing an anti-orientation from the stereochemistry. Cool. Okay, I'm gonna do my last little bit of talking. And this at least it has a little activity, and then we'll do problems. So group 3 in our simple alkene reactions, the final one in our simples, are making alcohols. So if I added H3O plus, which of these alcohols would I make? Take a minute and while you think. The whole thing. So on the count of 3, say what you think it is. 1, 2, 3. Wow. Okay. I can't trick you. I can't mess you up. You know what you're doing. So the important thing that happened here is we caught this carbocation, and then what occurred? A methyl shift, exactly. And so what we see is we did quote a kind of Markovnikov. We added to a more substituted side, but we had a rearrangement where more substituted side shifted. So what should we do if we want this specific alcohol, which is our plain Jane Markovnikov, no rearrangement? Well, we have a reaction for that. So our reaction that we are going to use for the Markovnikov with no rearrangement is the oxymercuration reduction. Ooh. So the way I think of it, and this is again very stupid, is Mercury, the planets, orbits, order, no rearrangements. No rearrangements. Look to the planets, the order and the star. It's really stupid, but I've memorized it now. So if that helps you. Okay. Now, no. So this is the Markovnikov product, right? What's weird about this product in the bottom? Anti-Markovnikov. We've added our OH to the less substituted side of the alkene here. And so what we use is a reaction called hydroboration oxidation. So she has boron. I call hydroboration oxidation HBO. And I like to think like she's not like other girls. You can't get away with this on cable. She goes against the grain. She goes against her expectations. She's really trying to get that Emmy. And so she's doing, you're watching John Tucker Must Die, Anti-Markovnikov on HBO. Again, there's a method to the madness, but it truly is madness. So you can see how we have some flavors for adding alcohols and why we might want to use some over the other, because you have situations like this where you want to avoid rearrangement. And then sometimes you want to actually get the anti-Markovnikov product. This is our first anti-Markovnikov reaction. Wow. So let's quickly talk about the mechanism for this, and then we'll do the practice. So does this first step for the oxymercuration remind you more of the X2 anti-additions, or does it remind you more of the simple alkene acid additions? X2 anti, because we form our little cyclic ring. And whenever we form the cyclic ring, we have to attack from the opposite side, so we get an anti-orientation. So HGOAC, you can kind of think of her as like BRBR, but the kind of kicker is she has a lone pair on her, which is the thing that's going to attack, which is like the BR, right? So the BR had a lone pair attack, and then you went and attacked her. And then instead of kicking off a BR, you kick off one of these OAC groups, these acetate groups, which really look like this. The OAC is just faster to write. So we do it that way. And then here we have mercury with positive charge, which is like an epoxide acid. We attack the more substituted side with some nucleophile, and then we have it anti. And so what our nucleophile is depends on what our solvent is for. So we can do the oxymercuration here in H2O. And if we do it in H2O, then we've added an OH here after deprotonation. So that's our nucleophile in H2O. But we can also do this in alcohol. And if we do it in alcohol, what we wind up with an OR here. So what functional group is this? If we add an OR, what functional group is this? Ether. And I really wanted to make it this dramatic big reveal of like, remember I told you to watch out. Those ethers are sneaky. There are going to be more ways other than the Williamson ether and the acid to make ethers. There were epoxides and this. I really wanted to be this like, her, she's here, spotted, ether. But it's just not that dramatic. And so I'm going to try to let go of that, you know? It's just not going to work. Yes, we found another way of making an ether. Great. So what I've done on the wheel is I have two versions of this. One where you add an OH, one where you add OR. But what do you guys about this boy that's kind of weird? What does that mean? Yeah. And actually for this carbon, does it matter? No, because it's not stereochemistry. It's not stereocenter. But I did want to notate it to just clearly show what two things were added. But it has to do with the second step, which is why we don't know. So after the first step, we do know for sure we have added anti. But sodium borohydride, she is going to scramble the stereochemistry here. It's because she uses radicals. You don't need to know the mechanism at all for it. All you need to know is it scrambles it. And so I had some stupid mnemonic of like Mercury, astrology, scrambling eggs. Wow, it's really gone. I guess it probably wasn't very good. Yeah. Or sodium, you put salt on your eggs when you scramble them, maybe. Again, are you really reaching to make this any more interesting than it is? Because it's horrible. So at the end of the day, even though we have this anti-step and anti-mechanism leading up, we get a mixture of syn and anti for our products. Moving on, HBO. HBO, go. So we have BH3. And what we're going to do is this concerted mechanism where our alkane attacks the empty 2p orbital on the boron. And then just like we had the BH4, like we had BH4 minus, and we could do a hydride attack, that's kind of what happens here. So it's like we start to form that fourth bond to a boron, and it starts to become minus. And the hydrogen says, you know, I'm going to leave before things get bad. I'm just going to hop over here, and then we're done. Now, what do you notice about here who added to which side? Like, the more complicated thing looks like it's added to the less substitute side. But do we care about complicated? What do we care about? Which one's more electronegative, hydrogen or boron? Hydrogen. This is the flipping the script. You're not going to find this on cable. It's only on HBO. So once you are doing it here, this is another one where when you have your alkene, because the molecule is coming from one side and you are reacting at the same time and adding both things, you are only going to get a syn product. They're only going to be on the same side together. And then the second step replaces a BH2 with an OH. You don't need to know the mechanism, but the big thing is it retains stereochemistry. There's no scrambling. There's no censoring because it's HBO. HBO. That's the metaphor I'm trying to make work here of like scramble with Mercury, but order, no rearrangement. But here you keep the order, it's syn. Also, HBO shows a lot of syn. Like syn. So find whatever way will work for you to like get those straight in your head. But let's do some practice here. So some of these are skill builders. The first two are just writing through some mechanisms. So the first one's the oxymercuration with alcohol, which I don't think you actually did a full one in lecture of this. I think Ken was like, oh, it's just a second. And then the next one is doing this HBO reaction, but it's using BD3. Treat it like it's BH3, and then you'll just wind up with a D added, okay? Where the H would be. The last one I want you to try on your own here is this is challenge problem 1C, where you're doing a little mini synthesis that's like a few steps. And I want you to try doing this only with reactions we've talked to up until this point in section. There is one reaction that you can do that will go directly there. That is something that is like later on that we have not talked about in section yet. So try to do it and with the reactions we've talked about. And very last thing, draw out what the H3O plus product would be for this if we did H3O plus rather than the mercury. So I will be taking attendance while you do that because I think I know everyone's name. Except for, I don't know you. What's your name? Brianna. Hi. Okay. Yeah. Where are you over there? Where are you? You're okay. Where? You took them out. Okay. We have Hampton. Then we have Elizabeth Resner, which I don't know why I refer to you as a double name. But I do. Then we have Alex. And you're Alex O'Donnell, right? Okay. Are you the Sophia Sofiy? Or are you the other Sophia? Sofiya? Shishlakova? Work. Okay. Okay, then we have Jackie O. If you get tired of that nickname, let me know because it's going to be happening every time. Then we have Suji. And we have so the show. We have location. So, Keisha, do you ever come to my 8 a.m. or are you always in 10 a.m.? Heard. I just want to like move it to that roster for me. That'll be easier. Leah. Is that the way it sounds like? It's not like a hell yeah, but okay, but because I keep just thinking like hell yeah. No, hell yeah. Work. Okay. Andrew, do you still come to my 8 a.m. sometimes? Or are you 10 a.m. right now? Okay, work. The two dates are sitting down. Are you Tate H and you're Tate F? So the one of you who emailed me yesterday, I didn't respond. You're totally fine. Whichever one. You're fine. Michelle, do you sometimes come to the noon still, or are you always 10? Okay, that's fine. Yeah. Katie, are you Katie O? Krupa. Right. At least I know your name's Katie, but still. Oh, and you always come to my tent, but I have you on my noon roster. That's correct, right? You're always. Also, please feel free to talk to each other. Otherwise, it's just sad. And Nene and then Rafi. And also, Abby, do you sometimes still come to the 12? Okay. Work. Welcome, we're happy to have you. Ugh, I don't have to pass around the sheet anymore. This was just a necessity because I only have like 3 more pages. So that's why I have to remember it. So, you know. Okay. I'm gonna put up the answers for this. And then we can ask about it. Then we will work the bottom 2 problems together. So. Something like this. This first one should mostly be just like regurgitating arrows, and the kind of questions that I anticipate y'all having are things about like the stereochemistry. Like here, we would add this on a wedge, this on a dash, and we would have the plus minus because we also have the version where this is on a dash and this on the wedge. But why do we not need to care about this? Not a stereocenter, so we can just write it as a line. And so then we'll get a product where you have the dash version and the wedge version. In the one that they gave you here, they didn't give you stereochemistry. And if we don't give you stereochemistry as a product, you don't have to account for it. But I did the stereochemistry version so that you were thinking about it for the questions where you do have to account for it. Also, if you add a H3O plus, what you would get is you would have a carbocation here, and so you'd have a little hydride shift. So that was this like little thing that you're trying to avoid when you do Mercury, the order, the planets, no rearrangements. Then for the BH3 THF, so it's the same thing as BH3, but we're now doing it with deuterium D. The D adds to the more substituted side, and specifically it's syn addition. But again, we have not a stereo center. So all we get is here a stereo center here, and we have a plus minus because we could have added it on a wedge, or we could have added both of these on a dash. And then we replace the BD2 with OH in the second step. Now the key does things about like poly like boron structures of like, well, then after that, your BD2 starts doing things, or you start, or once you get here, you have BDT, and you would have another alkane come along, and you would do this. Okay, the boron deuterium bond attacks here and does this, and you like form this big cluster. Don't worry about it. It's a thing that does happen, but we will never ask you to write it in this class. It's more of putting on the skill builders to be like, FYI, it forms a big structure. And so other OChem classes care more about that. We don't. So I just wanted to put that there as like a note. Then finally, we are going from an alkene to adding a bromine. And we also add a hydrogen. And what's weird about adding this bromine? Or what's notable? So did we do Markovnikov or anti-Markovnikov? Great. What is the only reaction we've talked about so far that is anti-Markovnikov? Yeah, hydroboration oxidation, HBO. So if you do that, then you're at an OH. And then what reaction did you learn that takes an OH to a Br? Bruh, I like my alcohol. PBr3, PBRs. Yes. So there is one reaction that you could do this in one step with radicals. We typically don't prefer it for a synthesis question because like radicals can lead to a bunch of different products. And also because what was the problem, or what would happen if we had like a carbocation here? I'll draw it actually in a different color. So if we made this carbocation, what would happen? Yeah, so we have that ring strain. So we would open up the ring and have this, and then we would have a shift over. And this is the one that we did in the other section. So I'm going fast just because we did it last section. This is what would happen. When you do this reaction, you are doing it with radicals, and radicals are going to do similar things to the carbocations. Again, we'll explicitly talk about it on Friday, but just know to avoid that, we can use HBO, which is not going to do the rearrangement. So last type of problem down here is on challenge problem 8. This is a problem that like is deceptively more challenging than it looks. So for these reactions, we have to kind of go backwards and think where our alkene was. And if we don't think about this too hard, this is going to be pretty easy. Like if we didn't think about it too hard, we could be like, oh, okay, well, I did an alkene here, or I did like an alkene here. But it's actually a bit more nuanced because aside from that, if we have the alkene here, we can have the version where these two are trans to each other. And we can also have the version where these two are cis to each other. And so we have to know where the alkene is and whether it's E or Z. So that's like a lot to do. And to answer that question, we have to rely on what we know about the stereochemistry of the reactions. So let's do this bottom one together first. So BH3THF, what two things does it add to an alkene? A hydrogen. And at the very end, someone said BH2. What is it? What is added after step 2? OH. Great. And how do these two things add in terms of stereochemistry? Syn. And then we also know that's anti-Markovnikov, which I just write anti-Mark because it's very like John Tucker must die, Mark must die. Good. So that's our 3 things for this reaction that we know. So what we need to do is we can either say that, hey, this hydrogen that's over here is the hydrogen that we added, or the hydrogen that we added is the hydrogen over like here, like one of these. But also, because we are rotated, we can't clearly see which one's syn or anti, first of all. But we can kind of settle this actually by using our anti-Markovnikov. So let's say hypothetically, I'm going to draw the 2 alkanes that you could form. This one or this one. Between these two, does anyone have an instinct for you think it's A versus B? And I'll just say, can you say what your gut instinct is on 3? 1, 2, 3. Interesting. So let's talk about it. What is the more substituted side of the alkene for A? Is it going to be the left side or the right side? Left. For B, what's the more substituted side of the alkene? The left side or the right side? They're equally substituted. So when you do this B version, you don't have a more or less substituted side. Each one has a single H on it and then like one alkyl group. And so sometimes you're going to add to the left side, sometimes you're going to add to the right side, but you'll get a mixture of products. So if we only want to get one product, should we use B or A? A. Okay. So we know our double bond needs to be here, and we know that the hydrogen that we care about is this hydrogen, right? But also the way it's written out is this hydrogen is on a wedge and this OH is on a dash, but these are supposed to add syn. And so we can't really see the orientation of how we have added this. And so what we have to do is we have to rewrite this where we put the H and the OH in the same plane because they added syn. So this is that skill that we did in lecture 4 for the stereochemistry in the plane of rotating around the single bonds. So can you rotate around these bonds and see what goes on the wedge and what goes on the dash for each one? I want you to just try it on your own for like 30, 45 seconds. And just try to do that mental rotation in your head to see what adds on each one. And if that is a very hard skill for you, don't worry. I'm going to tell you the model kit version of this in a minute. It's always the thing of I want you to have the paper skill, and then we do the model kit. Is this what you got? Or did I make a mistake? Because I very well could have made a mistake. So the one on the right, the OH is kind of going away. Like imagine this is the plane and the OH is coming away from you. So all we're doing is moving it like this. So if the OH is coming away from you here initially, and you move it up like this, well then the H that was up here, you're going to rotate a little bit forward. And so it goes down on the wedge. Yeah, I'm saying we are redrawing the exact same molecule in a way where we can clearly see that this was a syn addition. We've drawn them both in the plane and they're both adding on the same side. And so we're doing a rotation of just redrawing this so we can more clearly see that. So like this rotation of going from like being back to being in the plane, that's like 60 degrees. That's not going to rotate fully 120 and switch all of them. So it's just going to be rotating from back to being up in the plane. I'm going to take the up in the plane one to being, or sorry, the up towards you to being a down towards you. And then it's going to take the down in the plane to being a down back. I know this is probably a weird skill, but did people who tried it, did some people get this? A few. This is again the same skill that you did before. I'm going to show you the model kit way in a minute. But once we've written it this way, we know that these two things added syn via our reaction mechanism. So what that tells us is the two things that are on the wedge are going to be on the same side of the double bond, and the two things that are on the dashes are going to be on the same side of the double bond. So what we can do from here is say, okay, we have our CH3 and H over here, and we have our ethyl and ethyl over here. And that's how we know we made specifically, or we started specifically with this alkene and not the trans alkene. So I'm going to say not this alkane. That's subtle. That's really nuanced. Let me show you the way to kind of think about it here. So I'm going to rotate this molecule here, where just based on how it's rotated, you can't really see whether these things added syn or anti, right? So all we could rely on is our knowledge that this reaction adds syn. So I'm going to orient it so that the two things are in the plane together. With me so far? So what we can do with the model kit, which I really like, is just imagine these folding down. And then you form a double bond here. And when you form a double bond, these two groups, which I have, these are going to be the ethyls, they're on the same side. They're cis to each other, right? So I'm going to do that transformation again. So like we started out, we didn't know what was happening, but we know that the reaction from our study of the mechanisms, we know it's going to be a syn addition. And what we can do is we can just kind of fold it down inwards. And then suddenly we have our alkene. And our alkene has those ethyl groups that I have in blue here, cis to each other. So if you have a model kit and you want to build something like this, like a simple one, where it's just two carbons and then you have like the same things attached to it where you can just rotate easily, doing it on this to me is really easy because you can kind of fold it. Whereas like you can imagine if I swapped the dasher wedges on one of this, then when I oriented it like this, you would get the trans version if I swapped one of the dashes or wedges. So it's a subtle kind of stereochemistry skill, but it's one that you can do. It just takes a little work. So can you try doing it for this one above it with the I2? So what you're going to want to do is start with the analysis of does it add syn or anti, what two things does it add, and is it Markovnikov? Figure out where the double bond's going to be, and then write out the two things in the plane that were added, either syn in the plane or anti in the plane. Now, I2 we didn't talk about, but what reaction does this look like? Cr2 or Cl2. It's exactly the same. So take a minute and try this out. So for your analysis step, you should get that this is our X2 anti addition. So it adds anti. The two things that you're going to add are i's. And it adds Markovnikov. And you know that just from the reaction mechanisms from the tree of reactions that we've learned. It's not anything deeper than that. So since they add anti, you want to draw your molecule so that your two i's are in the plane. So if we do that, what do we put on the dashes and wedges? So did you even have to do a rotation for this one? No. So I gave you all the easier one. I did the harder one with you. I hope that's okay. So here, now I want you to do the analysis here to figure out what two things are going to be on the same side of the double bond and try to draw what the starting material was. And then I will do it, okay? Take a few seconds and try to draw what two things are going to be on the same side of the double bond. So your two things that were on wedges should be on the same side. And two things on dashes on the same side. So that is how we get our starting material. Now I will go ahead and tell you there will be one box problem that's like this on the second exam. And to be very honest, if you like don't want to do this skill and you said this is too much for me, I don't like stereochemistry, getting the wrong stereoisomer would be -1 out of 4 points. So if you're okay with losing that and just not doing the work for this, sure. I shouldn't say -1. It could be either -1 or -1.5, something like that. But it's a skill that, especially if you just bring a model kit, it could be really quick and easy. Easy, breezy, beautiful. But Angel. Because it's this situation right here where this, I think. So I put these purple things I added in the plane. And what I'm going to do is I'm going to fold in like we have a double bond here. And then you see that these two things that were what I called like the ethyls, they are on the same side now. So doing it one more time. Now I'll do it so that the ethyls are pointing towards you, like they're on the wedges towards you. If I fold in and like turn around, now you can see that they're on the same side. So it's really just like this is a on paper rule that tells you what's going to happen when you kind of rotate this. Also, if you use the outcome in second language books, there are other ways to do this that don't put these two in the plane. This is the one that I find easiest for me. So if you want to do another system, you can do another system, but we spent a lot of time on this, so I'm going to move on. I can answer any other questions about it at the end, but we are done with the simple alkene addition reactions. So let's move on to the complex alkene addition family. So with the complex ones, remember we're more focused with line reactions. The first one here that we're going to talk about is ozonolysis. So for ozonolysis, does this look like our normal alkene addition where we like add two things and we have words like Markovnikov and anti-Markovnikov? No, she's here to mix things up. She's here to make a statement. She is here to break open the rings. Lord, split me open. Like this is truly like a wild and crazy reaction where we're going from being in a ring and a double bond to breaking both of those bonds in the double bond and plopping on carbonyls. We're going from the alkene reactions where we're doing all these like things with like halogen stuff to a carboxylic acid. We could turn that into an amide. Plop DCC in there. We're in business. This is going to radically shift you to a different set of reactions when you do an ozonolysis, which is why we love it. So the piece set this weekend, I think some of them use ozonolysis. If you ever need to open a ring on a synthesis, make a double bond, bust it open, Lord split it open on a synthesis with ozonolysis. So ozonolysis, you do not need to know a mechanism at all. What you need to do is have a safe mechanism to write the product. So our fake mechanism is erase the CC double bond and plop on carbonyls in the place. Now, if we are in quote reductive conditions, we are done. If we are in oxidative conditions, we take any aldehydes to a carboxylic acid. It's that easy. It's not super crazy. So what do we mean by reductive conditions and oxidative? Oxidative, it has O's. It's H2O2 for the second step. Reductive conditions, we use dimethyl sulfide, which we can write as Me2S, or I like DMS because there are fewer lines you have to draw. So reductive conditions, you stop at aldehydes. If you form an aldehyde like this, because that's this hydrogen over here is the one that's on the aldehyde. And then for oxidative conditions, you go all the way to carboxylic acid if you form an aldehyde after step 2. So take exactly 90 seconds and try to do these disconnections. Oh my, brand Jeopardy. Wow. 5 seconds of this great music. It's 30 seconds. Okay, so how did we do? The kind of like, ooh, I'm trying to trick them was the last one where you get the same for both oxidative and reductive because you have no hydrogens on it. Like you are going to form ketones both times, so you can't do the oxidative step where you take it to a carboxylic acid. Yeah. That was that was I'm so sorry. So I used to music direct and like conduct, and so I'm a because I have to cut through the band, you know? Wow, that was aggressive. Correct. It's only gonna, I did this as a trick as well, which is why I snapped because that was my trap. It's only gonna break open normal alkenes. It's not gonna break up an aryanids. Okay, any other questions on these? Yeah. Yeah, so when you cut them and put on the carbonyl, that's what happens for reductive conditions, right? And then oxidative, if there's an aldehyde, you take it to a carboxylic acid. Is there an aldehyde? No. So we can't take it any further. Yeah. Totally. So work. That's the first one, ozonolysis. She's pretty easy, line reactions. Osmium tetroxide. Great, I hate it. So, mechanism, we would never ask you this on a test because you do one step, then you have this thing stuck on it, then you would have to do a random second step to like wash it off. No. So, you really only care about this as a line reaction. And what you make is a vicinal diol, also known as a glycol. So, importantly, these add syn. And the reason they add syn is because imagine this big thing is your osmium nonsense. This is your alkene. The osmium nonsense is going to come and interact with only one face. It can't interact with the top face and the bottom face. And so we're going to get a syn, quote, quote, Markov glycol here. And you might be like, oh, Colton, I remember learning about glycols because I know all the reactions. I'm obsessed with the reactions. I've seen the glycol in lecture 7. What reaction made the glycol in lecture 7? Janasa. Stunning. So if you had an epoxide, and I guess I'll do this specific epoxide. You could do this version, or you could do the dash version, and you could use either H3O plus, or you could use NaOH H2O. Both of them would work. And why would this form anti instead of syn if we did this epoxide version? SN2, and you're having to attack the antibonding level. It's exactly like the anti-additions where if your bond's going this way, you have to attack from this side. Like if it's up like this, you have to attack from the bottom. And so you're always going to get anti over here versus this one's syn. So if we gave you a line reaction problem and you wound up with the glycol and we gave it to you syn, you have to use osmium. You cannot use an epoxide. If we give it to you anti, you have to use an epoxide. You can't use osmium. And I'm going to ask you a really mean question. Are you ready for me, B? What if I started with the glycol and added these reagents? What functional group would I form? Wow, okay. Y'all are just on a different level, I guess. Yeah, you would form an acetal. I thought I'd tricked you. Sorry, didn't. Very proud of you, I guess. So yeah, if we have a carbonyl and alcohols and acid, we form an acetal. And so that's one thing where like it's combining and putting into dialogue this lecture 3 reaction and a lecture 8 reaction. And you're like, oh my God, I didn't know they were friends. And they're like, yeah, we hang out, we get coffee every Tuesday. Yeah, we're best buds. So again, this is kind of how we're going to take these reactions and talk about it from a line reaction way and compare it to other things we've seen before. Then we have not osmium tetroxide. I have my typo here. So we have epoxide formation with peroxy acid. Again, please excuse the renovations. We're trying to better serve you in the future. We made an epoxide. How did we make an epoxide in the other lecture? What functional group made an epoxide? A halohydrin, right? So we had like an OH and a Br, and we added NaOH. So that's our lecture 7 version. Bless you. But now we can take an alkene and make an epoxide with MCPBA, alphabet soup. But you also now know how to make a halohydrin, don't you? So what reagents could you use to make a halohydrin from an alkene? Thank you. Someone was listening when I said, keep that in there for later. It's going to come back. Yes. So we could do this 2-step route and make an epoxide, or we could go directly there. And this is why this is my favorite reaction in this course, MCPBA, which is why I hate that I messed her up here. MCPBA is iconic. MCPBA is a single like word, phrase, name reaction. It's a Beyonce-like figure. This is an Adele. MCPBA. She is here. She is not about nonsense. She is trying to do things efficiently and get them done. And look at this. This is iconic. You're doing 4 arrows in 1 step, and then you're done. It's a 1-step reaction, but look at her go. And so part of it's just like, I just think she's neat, you know? Yeah, this is my favorite reaction in the class. I don't have a better reason other than she subverts expectations and she's very efficient and she does a lot. And I relate to that. Mm. So yes, the only thing that you need to know is other ways to make epoxies. Now you know 2 ways to make epoxides. Other reactions in this family are carbonyl additions, alkene reduction, and the radical bromination, which I'm not going to explicitly go through. Radicals we'll talk about Friday. Carbenoids, they're just kind of their own thing, but you're mostly going to just do them as line reactions. So if you form like a cyclopropane or cyclopropane with chlorines, you just use these line reactions, and there's nothing special. They're not related to any other reactions from the course, and so they're just kind of one-offs. And then if you want to just kind of dissolve away an alkene and make it into an alkane, use H2 palladium on carbon, and it adds SIN. But that's about it. So we're done with the alkene addition reactions for the most part. Are there any alkene formation, like alkene addition reaction questions? Or so last section, let's talk about the Wittig. So say it with me, Wittig, Wittig. If I catch any one of you saying, can you help me with the Wittig reaction? I'm gonna say, no, I can't, because I don't know what reaction you're talking about. So sorry. But if you want to try again later, then maybe. So you're doing the Wittig reaction. And the reason that she is iconic and special is because not only does she make an alkene, but she makes a carbon-carbon bond and takes her to an alkene all in one big reaction. So what we do is we start off with 2 functional groups. An aldehyde, you've seen her. An ylide, you've not seen her. So an ylide is just, we have a negative on a carbon right next to a positive on this PPH3. So that is an ylide. And what this Wittig reaction does is it takes the carbon components of both of these and makes a double bond between them. So like if I star this and box this, we have a double bond that's created between the star and the box. Iconic, stunning. Now, this is one, I call this reaction the boxy boy, and you'll see why when we get to the mechanism. And it's very like fancy Squidward. That's the vibe of this reaction. A little hoity-toity, but also kind of magnificent. This is one of 2 reactions in the course that will make alkenes. The only other reaction that makes alkenes is elimination, E1 or E2. So if you make an alkene or you see an alkene on the test, then you must have done either Wittig or elimination. And then also once you do an alkene, you can do like 20 other reactions because you have the whole web of reactions to do. So very powerful. So let's talk about this ylide. Just like when we did the Grignard, we had to talk about how to form the Grignard reagent. We have to form our ylide, and we form it from an alkyl halide. So first thing, to make our ylide, we need the PPH3 and we need a negative charge here. So step 1, PPH3, you add it via SN2 backside attack. Fair enough. And so we are halfway there to our ylide. And then all we need to do is a deprotonation here. So we use N-butyllithium just as a strong base. So it's going to come over and deprotonate right next to this positive charge. And then that will form our ylide. Any questions about ylide formation? Yeah. We want to do PPH3 specifically. Essentially, if we do other R groups that are less bulky and like don't orient things the right way, phosphorus can get into some trouble. That's the short version. Okay, let's see why it's called the boxy boy. So we formed our ylide, we have our carbonyl. You do the thing that feels so natural at this point. A nucleophile attacks a carbonyl electrophile and then push out. Well, isn't that quaint at this point? Well, like early childhood memories, attacking carbonyls. So when we do that, we've created this new carbon-carbon bond here. And then we have an O minus that's just kind of right next to the PPH3 and opposites attract. And so we get a situationship that happens and we form a box. But then they are really like, hey, this is not working out for us, so maybe we should go our separate ways. And so they just very calmly and peacefully take the box and just, whoop, they just do a, whoop. They fold in on either side, and what you get left with is this bottom half becomes the alkane, and the top half is OPPH3, which is just a byproduct. You don't need to worry about her. How iconic. This is like the ASMR satisfying of like reactions for organic chemistry. It doesn't get better than this. So if you don't think this is good, don't become a chemistry concentrator. But yeah, Boxy Boy reaction. You formed a little box and then you formed out. Okay, yeah, Boxy Boy. So this is really helpful for us because it lets us make some of those alkenes that were hard to make in eliminations. So what do you remember, like, what type of alkenes were more favored for elimination, terminal or internal? Internal. And what type of alkanes were favored for internal, E or Z? E, right? So Vidig is great because it prefers to make Z alkenes, which we don't have a way to really select for. And it's really easy to make terminal alkenes. So to make a terminal alkene, what we could do is we have like our two components on either side, right? Like, so to think about the two things that came together to make this terminal alkene, we divide down the middle and we make one side a carbonyl and the other side we make the ylide. So for this synthetic disconnection, we can do it either way. We could make this side the carbonyl, in which case you have a little aldehyde. Or sorry, that would be this aldehyde if you did this. And then the other side, you have a carbon with two H's, and you need to connect it to a PPH3 and do a plus minus, and that makes your ylide. Also, pay attention to the synthetic disconnection because you're about to do this on your own. Oh my goodness. So this one would be a perfectly valid way to make a terminal alkene with this ylide and this carbonyl. The other way you could do it is cut this way and put your carbonyl over here, in which case the two hydrogens here, it becomes formaldehyde. And on the other side, you have a minus and then to a PPH3 plus, like this. So either of these options work to make terminal alkenes. And then if you were doing truly any Vidig reaction, it's going to prefer Z. It only does Z. Cool. Cool. I just had to tell you because like I don't like lying to you and we lie to you so much. Yeah, like once you get into like upper level organic chemistry, they start saying like SN2 isn't a thing. They say it's really kind of more of a spectrum between SN1 and SN2. This is like 60% SN2. I know. So try the synthetic disconnection here. So for these two synthetic disconnections, what I want you to do is you do option 1, where you put the ylide on the top side and the carbonyl on the bottom side, and option 2, where you put the ylide on the top side, carbonyl on the bottom side. You got this. The timing of this section here is so much better. I was so sleepy this morning. But don't ask, don't tell policy. Oh my gosh. My friend that's starting med school this fall, I sent her the alkene thing to look over, and because she has a good like stylistic eye, and she just texted me all caps. She's looking beautiful. She is. She really had to glow up. then once done with this connection, and then try this last one, where you're connecting. How'd you do? But I should probably ask, how did I do? Because two brain cells left. So how did I do? The last call that we need to make on this is, okay, let's say for each of these, we have two options. I'm gonna call this option one, option two. And then we have option one here and option two here. How do we decide which option's better? To do that, we have to look at the ILID. So what happened when we made our ILID? What type of reaction? SN2, and what do we know controls SN2 reactions? Sterics. So if we had the choice between using a secondary ILID versus using a methyl ILID, which one's going to be easier? The methyl. So this pair is the better pair if you had to generate a best pair of the two to form it, because it would be really slow to form this. Okay, what about for the next one? I'm gonna just say option one versus option two, which is better. I'm gonna give you 5 seconds to think. It's better between option one and two. And you're gonna say it after three. 1, 2, 3. 1. Because here you have a primary ILID, and here you have a secondary ILID. Very good. So that's how you decide what the winner is. Now, would we take off points if you did the other one on an exam? Probably not. Like, I mean, I don't think that would be fair, but I don't know if I'm going to be grading this question. So I think both of them would be valid. Like, I mean, you could just do a slower route. Um, that's kind of all I have for you. Oh, wait, actually, I will say there's one thing that I will guess at least 15, if not more than 20 students will miss with a Vidic. Count your dang carbons. This is the type of reaction where everyone wants to add a random carbon, like poof, out of nowhere, or just like poof, disappear a carbon. No, 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 no. Every carbon that is in here needs to be seen over here. It's not going to be a situation where I think a lot of students would do this, and they'd be like, I made the ILID. I'm like, where did she come from? Who is she? Where's she? No, no. So just save me and you some time, save some points in the exam. Thank you for coming to section. Yeah, this was a very like me talking section, and so I'm gonna keep workshopping her. Also, if anyone has 5 free minutes and wants to help me get my pavement so I can have some food and coffee, I would appreciate you and pay you $5. So, oh my, oh my gosh, wow, wow. I will be around here for questions, and I'll see you in lecture tomorrow. Okay. Remember the survey if you haven't done the survey. Here. 1 second. Um. Okay, give me 1 second.